orthogonal set of vectors. Okay, Gram-Schmidt process, and that's a very important topic we will have to speak about. Okay, the Gram-Schmidt process is a method for also normalizing. So I will use this technique in order to get an also normalized set of vectors in an inner product space, in inner product, using inner product. It takes a linearly independent set of vectors. يبقى لو أنا عندي linearly independent set of vectors. Using this technique, I will produce an orthonormal set of vectors that spans the same subspace. Let me tell you once more. If I have a linearly independent set, if I use this method, I will be able to get the orthonormal set from. طيب, how to do it, Miss Nada? لا, ده محتاجك تركزي معايا. In order to do it, I will do the steps on U1, U2, U3. These are the equations. It may look at first as difficult ones, but I will do it with you step by step, then we will do through them in order to make your life easier in memorizing them. If I have U1, is this color clear for you? If I have U1, U2, U3, this is a basis belongs to R3. So how many vectors? 3 of them. They are linearly independent, but they are not orthogonal. I need to get orthogonal and also normalizing these vectors. It can be done. Very simple. I will start with the orthogonality. So I will choose my new set of vectors as V1. I will put it equal to U1. Then I will get the second vector. I need you to memorize. How am I writing? I will write negative, then I will have a division of the inner product of V1, this vector, divided by the magnitude of V1 times V1. Of course, this value is a number. So once you have this value multiplied by V1, you will have a vector. What's remaining here is the elements, this guy, and what's going to be a dot multiplication in V1. I will use U2. So this is U2. Now I have V1 and V2. This is how to memorize this method. I will get the third component. Let's write it together. Looks like this is the third vector. How to get it? I will write minus sign, then I will write the fraction, also V1 divided by the magnitude of V1, not V1, then minus exactly the same, but not with V1. I will do it with V2. So it's going to be with V2 by the magnitude of V2 dot V2. Which vector I'm evaluating? The third vector. So I will use U3 that's the first vector, second vector, third vector, and these 3 vectors are orthogonal on each other. This is how to get an orthogonal set of vectors out of a general set of vectors. Are you with me? So I can get them using this relation. Do you want me to write it again? I will do it with you on the slides. Okay. So once more, that's the results. That's the result on the slides. This is V1 is equal to U1. That's exactly the same. V1, V1 squared, V1. Then I will write the second vector. For the third vector, I will repeat this part. But once with V1 and twice with V2. Using the third vector, which is U3, 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 you will be able to get your V1, V2, V3 which is an orthogonal basis for R3. This is how to get an orthogonal basis for R3 out of linearly of a basis. لأن أنت عارف طبعا, of course you know that the basis consists of vectors which are perpendicular, which are linearly independent. Farid, how to orthonormalize it? This is how to orthogonalize it. How to orthonormalize it? Then I will divide each vector of these vectors on its magnitude. Then V1 on the magnitude of V1, V2 on the magnitude of V2, V3 on the magnitude, so it's not going to be orthogonal, it's going to be orthonormal. This is how to orthogonalize a set of vectors and how to change them to be also normalized. Okay? So, once more, these are the steps of Gram-Schmidt process. So, of course, he's stating to you, let F be a subspace of the vector space R3 if the dimension is equal to 1. So, your subvector space was dimension 1, which means a subvector space, okay, from a vector space. But this group of subvector spaces, it has just only one vector, okay? Like for example, the subvector space 1, 1, 1, which represent 1, 1, 1, 2, 2, 2, 5, 5, 5, negative 1, negative 1, negative 1, 0, 0, 0. That's a subvector space out of R3. So I can generate the subvector space, which is 1, 0, 1. What's the subvector space 1, 0, 1? 1, 0, 1, 2, 0, 2, negative 2, 0, negative 2. Do you know what I'm saying? Okay, so now once more, let F be a subspace of the vector space اللي هو مين؟ R3, which is R3. Okay? If dimension F is 1, which means I will have a subvector space, but the basis is one vector, just only one vector. Is a basis for F. Then U1 is an orthogonal basis E dash for F. يعني الفيكتور ده هو نفسه orthogonal by itself. هيبقى orthogonal على مين؟ على نفسه. And orthonormal if you divide it by the magnitude of this vector. This is how to get a subvector space orthogonal and orthonormal direct. If I have another subvector space, but in this case, the dimension of this subvector space contain how many vectors? 2. It's like the subvector space of R3, which is 1, 0, 0, 0, 1, 0. It has how many vectors? 2 vectors. Huh? It's apart from R3, but with how many vectors? Or the dimension is 2. Okay? I can get an orthogonal basis. How I'm going to get the orthogonal basis? I will let V1 is equal to U1. I will use the Gram-Schmidt. Then the second vector is going to be U2 dot V1 over the magnitude of V1 times V1. These are the 2 vectors. Now that's an orthogonal basis for this sub-vector space. How to orthonormalize it? Those are orthogonal. How to normalize it? I will divide the first vector of its magnitude. I will divide the second vector. This is the second vector of its magnitude. Are you with me?
In the first statement, they said that U1 is one value, so remember that means if I multiply U1 times U1, it's going to give me 0, right?
Okay. U1 is one vector. Okay? So he's telling you that is a basis for F. And U1 is an orthogonal basis. Also, he represents an orthogonal basis for F. But U1 in itself, they are not orthogonal. It will equal to 1. Okay? But in this case, okay, he's telling you this vector by itself, it's just only one vector. So if you use Gram-Schmidt, you will have him by itself is an orthogonal set. So once more, please let me redo it once more. If I have a subvector space and it have just only one vector, this one vector is an orthogonal basis for this subvector space. It's not orthogonal in itself. It's an orthogonal basis for this subvector space. Okay, I have another subvector space, but in this time, My new subvector space contains how many vectors in its basis? 2, which is U1 and U2. From this U1 and U2, I can get orthogonal basis for this subvector space. How to get this orthogonal basis for this subvector space? Using the Gram-Schmidt. Letting U1 is equal to V1. Then I will get an orthogonal vector on V1, which is done by this guy. If I have a subvector space from R3, but the dimension is 3, then I will have to use, this is how to normalize. If I have V1, V2, V3, which is an orthogonal set, from U1, U2, U3, any basis of R3, I will form this guy. So the first component will be U1. The first component will be U1. The second component will be this guy. The third component will be U3 minus U3 times V1 over V1 squared times V1 minus U3 times V2. Are you with me? Okay? That's the third component. So those are going to be the 3 components which are orthogonal. If you want to normalize them once more, divide each one of them its magnitude. Are you with me? I don't want to move forward unless this is completely understood. Because if I move forward and this is not well understood, you're not going to understand it. Once more, I'm not getting an orthogonal vector on a vector. I'm getting an orthogonal basis for a sub-vector space. In the cases, if this vector space were R3, I will have sub-vector spaces of dimension 1, sub-vector spaces of dimension 2, other sub-vector spaces of dimension 3. If I have a sub-vector space of dimension 1, then the orthogonal basis of this sub-vector space is the same vector. If I have 2 vectors, I will use Gram-Schmidt. For the V1 is equal to U1, and then U2, you know how to get it. Okay, if I have the 3, I will use the 3 components. Okay? Okay, let's do this problem. Jana, Ziyad, Nada. I have U1 and U2. Nada. I have U1 and U2. Triple 1, 1, 3, 2. بيقول be a basis for subspace F of R3. Farid, is this an orthogonal basis? Is this an orthogonal basis? طب يلا وريني كده. 1 times 1, 1 plus 1 times 3, 3. The sum is 4. 1 times 2 is 2. So the sum is 6. دول orthogonal. So it's a basis لمين؟ subspace اسمه ايه؟ F of R3. أنا بقى دلوقتي عايز أجيب basis. I want to get a new basis which is orthogonal. Are you with me? يبقى now for the given, I've given you a basis for a specific subvector space. Miss Nada, these 2 vectors are linearly dependent. Look to these vectors. Are they linearly dependent or linearly independent? It's very simple. Very obvious they are linearly independent. Ya Fatin, why I called it, it's very obvious they are linearly independent. Because simply you cannot generate this vector from that vector. امسك لي 1 1 1 multiply, choose to multiply it on a number to make it 1 3 2. Can you multiply a number here to change 1 1 1 to be 1 3 2? You are not. So those are linearly independent vectors, which they are basis for subvector space, some vector space of F, which is a subset from R3. You know, one of the vector spaces, one of the sub-vector spaces from the vector space R3, with the basis of these 2 vectors, 1 1 1 and 1 3 2. Am I right? Okay. I need to apply Gram-Schmidt process in order to get استخدم دي عشان اجيب ايه؟ orthogonal basis يا جان. Let's do it together. Okay, I will let V1 equal to triple 1. This is the first step. V1 is equal to U1. So now, my new basis will be 1, 1, 1. Now I want to get the second, sorry. 1, 1, 1. Now I want to get V2. How to get V2? I will let V1 is equal to 1, 1 and 1. Then I will go V2 equal to minus V1 over the magnitude of V1 squared times V1. But I will write here U2. Let's do it step by step. U2 is 1, 3 and 2 minus 1, 3 and 2 times the vector V1, which is 1, 1, 1. On the magnitude of V1, which is a square root of 1 plus 1 plus 1. The result of this guy will be multiplied by 1, 1 and 1, which is gonna be 1 times 1. 1 times 1 is 1 plus 3 plus 2. The sum of all of them is 6 divided by root 3 times 1, 1 and 1. Then I will subtract this value out of 1, 3 and 2. This is gonna be V2. Okay? This is how to get a new basis for F but orthogonal. Okay? ماشي معايا شباب؟ Okay. So I will start once more. This is V1 equal to U1. هثبت الاولاني. معايا فاتن؟ هكتب التاني V2 بص اللي كاتب لك خلي بالك ان ده U2 اللي هو 132 هيتحط مرتين ادي 132 minus 132 دوت تريبل 1 مقسوم على الماجنتيود اوف تريبل 1 تايمز تريبل 1. If you do it انا برضه مش هقول لك عليه. That's gonna be 6 over I'm sorry طبعا لان في هنا سكوير روت فبدل ما يبقى روت 6 يبقى 3 يبقى ده 6 over 3. Okay, so it's gonna be 2, 2, 2. Make the subtraction. This is the new vector. Okay, stop. Log to that vector, which is V1. Log to that vector, which is V2. Are they orthogonal? Negative 1 times 1, negative 1. 1 times 1, positive 1. 0 times 1, 0. The sum is 0. So I began with F for a general basis. Now I have an orthogonal basis. يا جماعة, I want this basis to be orthonormal. What to do? I will divide the elements here on root 3 and the elements here on root 2. In this case, they will be orthonormal. And of course also. This is how to get an orthogonal basis for subvector space. Okay? Okay, very good. طبعا remember if needed V3 يعني لو انت عايز تجيب V3 افتكر ان V3 بيتجاب من هنا. ماشي الحال؟ اوكي. تمام زين؟ ارجع قول لي.
ايه رقم روت 3 وروت 2؟
ايه؟
روت 2 وروت 3. بنعمل ديفايد
على الماجنتيود دول كده orthogonal vectors. لو انا عايز اخليه يونت فيكتور اي فيكتور عايز اخليه يونت فيكتور ديفايد على الماجنتيود. الماجنتيود بتاع ده بكام؟ سكوير روت فيرست سكوير سكند سكوير ثيرد سكوير يبقى ده يتقسم على روت 3. تمام كده؟ طيب ده كده مش نورمال فيكتور. I'm sorry ده ما هوش يونت فيكتور. If I want to get a unit vector, I will divide on the magnitude, which is going to be a square root 4, negative 1 to the power of 2, plus 1 to the power of 2, which means root 2. Okay? معايا يا فريد؟ تمام؟ يبقى ده V1 و V2 as I told you. طيب supposing for instance لو انا عايز اجيب basis orthogonal basis لمين؟ ل R3. I will need another vector which is perpendicular on these two vectors. I believe 0, 0, 1 will do. So if you choose 0, 0, 1, another third vector, now I have three vectors which they can form, I can get V3 out of the third vector which is linearly independent with these two vectors by just substituting these values in this, in making substitution, and it will be negative 1 over 3, negative 1 over 3, and 2 over 3. Now I have a perpendicular basis which is V1, V2, V3. V1 is triple 1, V2 is negative 1, 1 and 0, V3 is negative 1 over 3, negative 1 over 3, 2 over 3. Now I can get a base for R3, not just a subvector space. Okay, now I'm going to talk about what's called an orthogonal complement for a vector space or a subvector space. Daily, once more, but before we continue. In the previous, we introduced number one, what's an inner product? Number two, the angle between two vectors. Am I right? The condition for perpendicularity or orthogonal vectors. Then we spoke together about how to generate an orthogonal basis for a subvector space or for a vector space using the Gram-Schmidt process. Now I'm going to talk with you about getting a new vector or a new subvector space which is perpendicular on a subvector space. So if my hand represents a subvector space from R3, now I'm getting a perpendicular set of vectors on this guy, okay, which is called the orthogonal complement. So the orthogonal complement actually is a set of vectors or a subvector space where its vectors is orthogonal on that vector. Now, this is not the only vector. This is also orthogonal. That's also orthogonal, and this one is orthogonal, and so on. All of these orthogonal vectors are called an orthogonal subvector space on this vector space. I can call them the orthogonal complement of this subvector space. Okay? So, if this is a subvector space, that's the orthogonal complement. Now the orthogonal complements, the orthogonal complements of S are the orthogonal set of vectors on the plane S, and they can form a vector subspace of R3. شايف الحركة دي شديدة جدا. Every plane of R3 passing through the origin is a subspace of R3, and you already know this. Okay, definitions. If F is a subspace of R3, then the set of all vectors in R3 that are orthogonal, زي ما أنا شرحت لك عليه بالظبط, to every vector in F is called orthogonal complement of F, and will be denoted or symbolized by F perpendicular. So if I have F, it's a subvector space. F with the perpendicularity sign, it means the orthogonal complement on F. The orthogonal complement of F, it is the set of vectors belongs to R3, such that U dot V is equal to 0. For every V belongs to F. All of them, they are the same. I'm getting an orthogonal set of vectors perpendicular on certain set of vectors. Okay, if F is a subspace of R3, then Ft is a subspace of R3 also. Remember that, and this is really very important, if you sum, if you make a direct sum of the subvector space and the orthogonal complement of this subvector space, it will generate the vector space. Hello? Tani. If I have, okay, the basis for a subvector space, and if I have a basis for the orthogonal complement of this subvector space, and you added them together, you will get the vector space. Okay? It's a direct sum. Do you remember how we added or intersected or union between two subvector spaces? The direct vector space or the direct sum is happen only when the intersection is 0 between two subvector spaces. So you can add them together and the result will be R3, which means once more, the dimension of a vector space is equal to the dimension of the subvector space plus the dimension of its orthogonal complement. And that's a check that we will do together. Okay? Okay, the dimension theory is already written. Dimension of R3 is equal to dimension F plus the dimension of F orthogonal complement. Okay, let's try to do this problem together. This is a very nice problem. He's telling you what is the orthogonal complement of W. W is a subvector space of R3 with a basis 1, 2, 3. I need the subvector space of this guy. It's an orthogonal complement, am I right? So all the vectors are going to be orthogonal on this vector. So I can say simply that the vector that I need, which is W orthogonal complement, is X, Y, and Z. Okay, those are the coordinates. And since W orthogonal complements on W, which means WT dot W should equal to 0. Am I right? So, which means X, Y, and Z dot 1, 2, 3 should equal to 0. You know the inner product, Miss Nada. That's 1 times X plus 2 times Y plus 3 times Z. All of them is equal to 0. Okay, which means X is equal to negative 2Y minus 3Z. Take this condition with you. Now I'm getting WT, the orthogonal complement, which is a set of vectors X, Y, and Z, belongs to R3 such that every X is equal to negative over 2Y minus 3Z. Miss Seda tried to substitute. So it's a negative 2 over Y minus 3 of a Z, Y, and Z, which can be easily separated into the given form. Am I right? Which is negative over 2Y, then Y and 0. And you will have negative 3 over Z, I believe 0 and Z. Am I right? Where Y and Z belongs to R, which the basis will be, this is the basis. It's gonna be, أو خلينا نستخدم احنا نفسي نستخدم العلامة دي, which is gonna be negative 2, 1, and 0. And it's gonna be negative 3, 0, and 1. These two vectors are perpendicular. صح? These two vectors, I'm sorry, they are linearly independent. And they are the basis of the orthogonal complement. What's the dimension, please? The dimension of this orthogonal complement? 1. That's two vectors. And W by itself, it has 1 vector. The sum of them is equal to 3 because this is R3. Am I right? So now I had the opportunity to get or to grab the orthogonal complement basis. Do you like this basis to be orthogonal? You can do it using Gram-Schmidt process. So, if you like. Okay. So once more. To determine the orthogonal complement of W, we already know that the vector is K1, 2, 3. It's the shape of any vector. Multiplied by X, Y, Z, the result will equal to 0, which means I will multiply the product between both of them. I will have X plus 2Y plus 3 equal to 0. Now I can use this relation in order to separate them and then having these two vectors, which is the span of the orthogonal complement. And the number of vectors here is 2, and the number of vectors over there is 1, and the sum of them is equal to 3. Okay, I can also do it in this problem, find the orthogonal complement of W. Yeah, madam. W has 2 vectors. Has 2 vectors. Yeah, Jana. How to find the orthogonal complement? The orthogonal complement of set of vectors, all I know, is XYZ. That's the shape of the vectors. XYZ times 1, 2, 3 is equal to 0. XYZ times 4, 5, and 6 is equal to 0. So those are 2 equations. I will solve them together in order to get the relation.
I can't put them all.
Yes, but it's difficult to put them all equal to 0. Because our understanding is these 2 vectors, and that's the orthogonal complement. So its relation with this vector, they are perpendicular. And its relation with that vector is also perpendicular. So I'm using this relation to build up my system of equations. So once more, I will do it. This is the first bunch, XYZ times 1, 2, 3, XYZ times 4, 5, and 6. It will lead you to these 2 equations and 3 unknowns. It's a homogeneous system. You can get the result. That's the augmented matrix. You can solve it to get the reduced echelon form, which means that X is equal to negative is equal to Z. And the Y is equal to negative 2Z. It's an augmented matrix for a homogeneous system. This is X, Y, and Z, which means X minus Z equals 0. So X is equal to 0. And this equation, it means Y plus 2Z is equal to 0, which means Y equal to negative 2Z. Now I can find the relation between them. I can use this substitution. لو انا استخدمت substitution ده طبعا السيستم اوف equations تاني. لو انا استخدمت substitutions دي في x, y, z, then I can separate the vector 1, negative 2, and 1. Remark, that's the orthogonal complement. That's the basis of the orthogonal complement. صح? This is how many vectors as dimension? And previously were 2. The sum of them is equal to 3. The dimension of the perpendicular orthogonal complement is the dimension of R3 minus the dimension of W, which is 2. It's going to be 1. So if you add them together in any manner, you will end up having the dimension of the orthogonal complement plus the dimension of your subvector space will equal to the the dimension of your vector space. Let F be a subspace of R3. لو ال F كان origin, then its orthogonal complement of U will be the origin, because U times V is U times the origin is equal to origin. If F belongs to R3 and the orthogonal complement is 0, then the orthogonal complement on the 0, the main subvector space on perpendicular or orthogonal on this origin is R3. So they are completing each other. If F is XYZ and you have X minus 2 over 3Z equal to 0, then 1, negative 2, and 3 is going to be the vector perpendicular on this condition. So if I use the substitution of X equal to 2Y plus 3Z and they make a substitution and try to separate them, I will get the subvector space, the basis of this subvector space. The orthogonal basis will be 1, negative 2, and 3, and they are here, 1, negative 2, and 3. Okay, I've wrote something about this. This is an equation of a plane R3, and its normal vector is 1, negative 2, and 3. This is what we are going to cover by the end of this week or the beginning of next week, which is the equation of a plane. Okay? So once more, 1, negative 2, 3 dot xyz, if you multiply them together, the result will equal to 0, which means it is a normal vector for this guy. Remember, this is one of the methods that we will use in getting a plane equation next time, inshallah. Okay, suppose the vectors u1 to ub of R3, the following are equivalent. خلي بالك من equivalent statements. W is orthogonal to each of the vectors u1 up to ub. W is orthogonal to each vector of the subspace u1 up to ub. That's W belongs to u1, ub, orthogonal complement. So to have a vector or perpendicular on a set of vectors as a basis, it belongs to the subvector space of the orthogonal units. Consider the following subspace, x, y, and z. And this is x minus 2y plus 3z equal to 0. We have, number one, if you use the substitution as I told you, this is the basis of this subvector space. That's the basis of this subvector space. If you multiply these two guys in x, y, z, in order to get the orthogonal complement and to solve the system, this is going to be the result, 1, negative 2, and 3. You will see it. Okay, remember our remarks. Normal vector is 1, negative 2, and 3, and it is perpendicular on both two vectors. Two vectors do. Span of these vector space and also dimension f plus dimension, the orthogonal complement is equal to R3. That's the two vectors, and the orthogonal on them will be one vector, sum is equal to R3. Confirmation of the previous remarks. How to get a normal vector on basis of two vectors. تاني أنا بعيد نفس الكلام. How to get a perpendicular vector on two vectors. I will do this way. These are that's the condition, multiplying x, y, z by 2, 1, 0, the first vector, and the multiplying x, y, z by negative 3, 0, 1 equal to 0. How many equations? Two equations. Solve them. You will get the conditions. Okay, I've tried to solve them together. These are the two equations. I've wrote the two equations for you. Solve this system of equations. If you solve them, you will get these two conditions. In x equal 1/3 of z, y equal negative 2 over 3 of z. These are the conditions. If you use these conditions and then make a substitution, you will be able to isolate z, and that's the vector that we are talking about, 1, negative 2, and 3. Of course, you remark that this vector, F3, is exactly that vector. Because you multiply it in 3, صح? So they are equal to each other. تفضل. Well, I've multiplied it by 3 in order to avoid that they are fractions. And already it's a basis. So that's the basis with this shape.